So let's keep going. So we are now entering the final section of this exciting course where we're actually going to start designing really cool algorithms for object recognition, action recognition, right, behavior analysis, and so on and so forth. So the very first thing that I want to discuss today, a couple of things I want to discuss today. The very first thing is how are we going to design the systems? What's the basic concepts that we're going to be utilizing for that design, and how to evaluate the systems, right? Because it's easier said than done. And I have to say, I always thought, or I keep thinking, that I should prepare a probably half a semester course on just evaluation methods, right? So evaluation is a super important component of any AI system, machine learning, computer vision, image processing, speech analysis, and so on. Very little is known by most of you and other students from other institutions, and I think that's too bad. I think maybe a 10 lecture course would be sufficient, but we certainly cannot do it in a lecture or less, as I'm going to do here today. I have to say, I do cover evaluation in more detail in my machine learning course, so you may want to go to the YouTube lectures and check those couple of lectures. I think it's lecture and a half or so where I covered that topic. But here I'm just going to have to simplify quite a bit. And believe me, in machine learning is already super simplified. So this is a simplification of a simplification, right? But at least you need to know that very minimum that we're going to cover here today, okay, at the very least. But note that you should know more if you can. All right, so the most classical way to design a computer vision system is to start by collecting data, right? What we typically call a data set. So we collect a data set. That's always, well, not always, but we'll get to that. But this is typically the number one step, okay? Data collection. That is fundamental. I cannot emphasize enough how important this is. In fact, these days, it's probably between 50 and 75% of the work in computer vision. It's just data collection, right? It's extraordinarily important. Now, it's interesting because in biology, for example, or in physics, they have known this for generations, right? For decades, generations of scientists. In biology, for example, they spent hundreds of millions of dollars to collect the first 2 genomes, right? And what were the collection of the 2 first genomes? Data sets, right? Just letters of the DNA sequence of a human. Physicists built a several billion dollar, right? Large Hadron Collider in Europe to just collide particles and collect data. That's how important data collection is, right? And it seems that in AI, it's taken us this long until very recent years to realize data collection is a super important component of what we do, right? So in my case, for example, in the late 1990s, I know, when you probably were born, I collected a data set called the AR-face database. We'll talk more about it. And back then, data collection was like, oh, okay, you collected the data set, so what, right? No one really gave it much relevance. Like, yeah, okay, now do some science, right? No, collecting the data set, and I'm going to talk in a later lecture more about this importance of data collection and how to create a good data set. Data collection is a super difficult and very important part of the both research or engineering if you work at a company, right? And if you don't have a tremendously good data set, your product that you're going to develop for that company is probably not going to be very good, right? When you see systems out there, in computer vision systems in particular, that work better than other systems, generally, it's not because of the algorithms. All these algorithms that we're discussing here, they are all pretty much equally good. Yeah, some are a little better, some are a little worse, but in general, they're all pretty good. The difference is in the data collection. The data those algorithms have used to learn, and we'll define what this learning means, what that task that we want to achieve is. Okay? All right. So what this means, right? So what this truly means is that we have a set, let me call it, I'm going to use this kind of mathematical X, right? So in LaTeX, if you go to MathCal, right? /MathCal X, it'll write this mathematical type of X. So I'm going to use this for set. And what this is a set, right? So I'm using the parenthesis of a set of, say, xi, I from 1, say, to n, right? So I have n samples. So these xi's here, right? These xi's, these are my samples. All right, so first so good. And I have n such samples. And then these xi's, right, so I can say where xi, for example, could be an image, right, of P1 by P2 pixels, right? So P1 rows, P1 columns, right, for example. Or maybe xi, it's a vectorized image of p pixels, right? So if the total number of pixels is p, and I scanned that image and I vectorize it, I put it as a vector, then I just have a p-dimensional vector, right? Instead of a matrix like this. Or, in fact, it could be not even a single image, it could be a video sequence, right? So maybe I have P1 by P2 pixels times t the number of frames, right? And that would be a tensor, right? I mean, they're all tensors. And that would be another tensor, a three-order tensor, right? That I have as samples of my data set. And so on, right? So, and so on and so forth. Now, to do this data collection has to be done with extreme care. The very first thing that we need to do before we even start thinking about data collection is to define the problem we need to solve. So first thing, define the problem. That's the very first step in any science or engineering problem, obviously. Define what your goal is, what you want to achieve, right? Because if you don't know what your goal is, then you don't know what data you need to collect. I mean, it's just, I know it makes sense, but you'd be surprised how many people first collect the data and then define the problem, depending on what that data have collected. That's completely wrong. So once you have defined the problem, you need to specify which images or videos, right? So specify the images or videos that need to be collected to solve that problem, right? Or to at least address this problem. Okay. Now, that could mean, for example, right? That could mean, for example, e.g., that is specify the resolution that I need, right? If I'm collecting images, that could just be the spatial resolution. If I'm collecting video, that might mean either the spatial and or the temporal resolution, right? What else? Illumination conditions that I'm going to consider. Occlusions, maybe. Am I going to consider that objects or actions or whatever I'm trying to collect for are partially occluded some of the time or completely occluded some of the time, right? And et cetera, et cetera, et cetera. Okay. Now, once you have done this, the third step is to determine how feasible, right? So determine the feasibility, right? Oops. Oh. No. Right? Okay. I'm lost. Oh, yeah, okay. The feasibility, meaning the cost, right? That's what I wanted to say. The feasibility, meaning the cost of the data that you need to collect according to step 2, right? And the cost can come in a variety of ways, or it does come in a variety of ways. Number one, how long is it going to take me to collect that data, right? If, according to the second definition or the specifications here that I need to solve that problem, I need to collect a data set that's going to take me 10 years to collect, then I probably need to reevaluate that, because maybe 10 years from now, this problem is no longer going to be important because someone else has already solved it, right? If it takes 100 years, then it really doesn't matter because we're probably not going to be alive in 100 years, so, right? That's for someone else to worry about. So obviously, time is important, but money is also important, right? I mean, usually you have a budget to create that data set, and you just have to abide by that budget, right? So maybe you can hire more people to collect more data. Instead of doing it in 10 years, you can do it in 5, maybe even in 2. But do you have the money? So if you have the money to hire those people, great, right? But if not, then you have to specify this. Now, once you have determined the cost, if this data collection, right, so if creating this database is feasible, right, then proceed, right? Otherwise, go back to step A, right? Go back to A, either redefine the problem or redefine B, the constraints to solve that problem, and repeat that process until you have a problem that you can solve with a data collection that is cost effective, right? Okay. All right. Typically, once you have done this and you have collected the data, the next step is to annotate the samples, right? So basically, you have to create that database that you just collected, right? That means organizing the data in a way that is easy for not only you, but everyone that's going to use that data to use it, right? So files cannot be named random numbers or random letters. They have to have some useful name. They may need to be in separate folders depending on what they represent, etc., right? You may need to write a README file, a report explaining what type of data there is, maybe a couple of routines on how to access the files and the data. So that's part of data curation, right? Another big component is what annotations do you need to provide for each of these images or videos that you have collected, right? So to annotate the data. Now, this data annotation is done because you want to tell your algorithms what's in the image. And what you're going to tell the algorithm, you're going to tell the algorithm what's in the image depending on what you want the algorithm to learn, right? So that means that you have to provide for each image, xi, some label yi, right? And that we said 1 through n, right? Some label yi that specify what you want the algorithm to know about that specific image or video sequence, right? Maybe if we're working on object recognition, that label could be the name of the object in the image, right? Now here, yi can be a natural number, right? It's rarely a set of characters like the word for the object, although you could do that. But rather what you would have, it's a lookup table that says 0 corresponds to table, 1 corresponds to car, 2 corresponds to what have you, right? And that way you go on, and then each number corresponds to an object category. Typically, you would do that with natural numbers or integers. Typically, positive integers. You could work with positive and negative integers. No one is preventing you from doing that, but just make sure that you follow some standard way, useful way. All right. So the other possibility is that these yi's are given by some real space of q dimensions. Okay? And that is the case when yi is just a continuous variable, right? Maybe what you are telling me is the size of the object I'm looking at, right? Which is a continuous variable, or the volume of that object, or the weight of that object, or the importance of that object in a continuous variable that is important for your employer, right? For the company you work for, and so on and so forth, right? Okay. Now, all of these, okay, hold on. This first one corresponds to classification. Classification because we put objects or images in our case and videos into boxes, right? Into natural numbers or integers, right? And we say this is 0, the 0 group, this is the 1 group, this is the 2 group. This is classifying things into boxes. Whereas the second case is regression, okay? Because we regress the function that goes from x to a continuous variable y, okay? And both of them correspond, in the case that we've defined it here, to what we're going to call supervised learning. Or supervised methods. And by supervised, what we mean is that we know because someone has labeled, probably us, although you may be using a database that someone else has collected, right? But in either case, you're going to use a data set that has these yi's given to you, right? Whenever you have this yi, this is supervised. Someone has told you, and therefore your algorithms, what these images correspond to. They have created the data set, they've organized the data set, and so on, right? All right. In the case that you're only going to use these simples here, these xi's, without the yi's, without having any human or any expert annotating these images or video sequences, then we talk about unsupervised methods, okay? All right. Now, we are not going to discuss unsupervised methods in this course. Maybe at the end I'll say a few things, but we're not going to discuss them in detail because this is something that's still in research, right? Still not sure how to solve the problem right now. But probably in the next 5 to 10 years, hopefully we'll have really good algorithms for that. So we're going to focus specifically on supervised methods, either for classification or for regression. Now, I have to say that for unsupervised, if you're interested and you read something in the literature, you have to be careful what it's meant by unsupervised, right? Because there are different ways to use the data that you have collected. If the data that you have collected has been curated in any way, this may be called either semi-supervised or weakly supervised, right? Because you have the data somehow structured in a useful way. So let me give you an example. Imagine that I collect a data set of handwritten digits, right? Digits from 0 to 9, okay? And I collect a good data set, huge data set, millions of examples of zeros, ones, twos, threes, and so on up to nines, right? And I have this great data set, but I don't label it. I give it to you. But I organize my data set such that first, you know this data set only has digits from 0 to 9. Well, that's some very weak, but some supervision. And not only that, I tell you that I've created the data set such that the number of zeros, the number of ones, the number of twos, the number of threes is identical. Well, right? You see where I'm going? So the more information like this that you have, the more supervision that you have. Yes, it's not technically supervised because I'm not giving you the YIs, but doesn't mean that it's completely unsupervised, right? Completely unsupervised would be something that I just collect random images from somewhere and I give them to you. No curated, not anything, right? Just random images. That would be truly unsupervised, right? Yeah, that's probably not this 5-10 years away that we're talking about. That's probably like 50 years away, right? Or 100 years away. So that's not what I mean by unsupervised. By unsupervised, I still mean that the data has been curated in some way, but the YIs are not given to me, okay? But I do know something. I know the problem. I know what the data contains, more or less. The data is pretty much balanced, so on and so forth, okay? And if it's unbalanced, I know what that imbalance is, right? Imbalance, excuse me. All right, so the other case could also be that you're only given labels for a small number of your xi's, right? So maybe you have a x1, let's say xi, yi, with I from 1 through n1, right? And then you have an x2, which is xi's, I from n1 plus 1 to n, right? And in that case, we talk about generally weak supervision, right? Okay, so we have some supervision, but just for a small number of samples. So weakly supervised in that case. Some people, some people also call this few-shot learning. Which means that you want to just train a system, learn from a very small number of samples, right? So you only want to use the capital X1 for training. And you can even go to the extreme and say, okay, I only have 2 samples per category that I want to learn, so it's a 2-shot learning, right? Or a 1-shot learning, which means you only have 1, right? And 0-shot would mean like you don't have any. Okay. Now, these sets, right, being it either this set here or these sets here or this one if you're going to do unsupervised, right? Any of these sets, these are called the training set. And this is called a training set because it's what you do to design the algorithm, okay? It doesn't matter if the algorithm has to be trained in the machine learning sense, but it's a training set if it's the data that you're going to use to design your computer vision system, right? Okay? All right. Once the system has been designed with this training set, and we wish to test how it performs, then we usually use what's called a validation set. Okay? Let's call it V. I'm going to use this mathematical calligraphy again. And here I'm going to have xi, yi, I from n plus 1, to say m. Okay? Now note that here in this set, right, I start from n plus 1, meaning that I have to have more than n samples if I want to validate how well I do. I cannot reuse any of the samples that I have used during the design of my system. I have to use a completely independent set of images or video sequences, okay? So it has to be from n plus 1 to say m. And if we're using a supervised method, then this has to be labeled, right? You have to have these labels yi's. And I need those labels yi's even if I were to use unsupervised methods for designing my algorithm. I need those labels in my verification set because otherwise I would not know whether my algorithm performs as expected or not. Okay? So in the validation set, you must have the yi's. And we'll see how to use them in a second. The alternative to, so there would be a step 3, forget to add this. The obvious alternative to designing or to providing this validation set is in the case that you know the true underlying function that your algorithm has to estimate. Now remember that most, if not all, of computer vision, at least everything I was discussing here, abides to the model f of x equals y, right? And that's why the samples xi and yi's are useful to us to design an algorithm that represents this underlying function. So for example, in low-level vision and mid-level vision, we talk about how to design camera models that model that f of the projection from 3D to 2D, so then I can go from 2D to 3D, right? As an example. This here can be substituted, this verification set, by the true underlying function I'm trying to get to estimate, right? If I know that. In some camera models, in some multi-view geometry problems, that may actually be known. Not known the true actual one, but a very good estimate of the reality of the world, right? And in that case, I can compare these two. Or in the case of object recognition or image segmentation, I can run simulations with synthetic data, right? And in that case, I know the underlying function. So now the underlying function, let's say h, okay? H function. Now, this function, if it's known, it's called the oracle, okay? Because that is what tells us, given xi, if I do h of xi, I get the yi for any xi, right? Okay? So formally then, meaning mathematically, you can write this as xi, and instead of yi now, h of xi. From n plus 1 to m, or maybe 1 through m if this is given available. Now, this validation set cannot be used during the design of our system or to train our system if we're using machine learning tools. But this validation set is visible to us, meaning I have it. I have that validation set in a file in my computer somewhere, right? Or in my system, my computing system. So this is visible to me. I can go there and peek, right? And this is what people do. People design a system, a computer vision system, right? And once they think it works, they test it on the validation set, and most likely, most of the time, it doesn't work on the validation set. So they go back and change, right? Reconfigured everything and change the algorithm, and then test it again on verification set. It maybe works a little better, but still doesn't really work. And then they go back and they keep changing and changing, right? Keep iterating this process until it works on the validation set, right? And that is fine, but you have to know that you are adapting your algorithm to that validation set, what people sometimes call overfitting to that data, right? And that's a problem because there's data out there that you've never seen for which your algorithm may not work. So although it's okay to repeat this process, the more iterations that you do, the less likely is that your algorithm is eventually going to work in the real world, right? Okay. One way to create this data set is to collect n samples, label the n samples like this, and then do what's called k-fold cross-validation. Now, k-fold cross-validation, what it means is that you divide your entire data set, this capital X, into k partitions, k subsets. You use k minus 1 of these subsets as your training set, and the last one as your validation set. Now, because there are k ways of leaving one of these sets out for validation, what you do is you test all the k possible sets that you can leave out, and then compute the average and the standard deviation of your algorithm on that validation set, this k validation sets that you have left out, right? That is one of the ideal ways to do that. Your validation set is still visible to you, but at least you keep changing the validation set, right? And if this k-fold cross-validation is done randomly, every time you modify your algorithm and you go back, the partition is different, right? And therefore, you are adding a little bit more of randomness into the system, and most likely the algorithm will work better. So always try to use methods like k-fold cross-validation when you want to create a validation set to test your system. And then number 4, just need one more. Maybe I can write it here. I don't want to erase this yet. Number 4, you need to test for statistical significance. And maybe I'll add the number 5. Number 5 is you need to test for statistical significance. Let me actually add the number 6. You need to test for statistical significance. And I want to emphasize this because almost no one does it. I don't know how many times I have read papers, even in top conferences and journals in computer vision, where they'll have this illusory table at the end of the paper in the results section where they say, oh, And on that data set, my algorithm performs, instead of this previous algorithms that perform 89% correct, mine performs 90% correct. Really? And is that statistically significant? I don't know, maybe it is, but have you run statistical significance? Have you checked? If you haven't checked, then I'm tending to believe that 1% better is not statistically significant. Because if I change the training and testing set, or rather validation set, right? The training validation set, probably your algorithm is going to be 1 point below the other current results, right? So, yeah, no. So there are many ways to test the statistical significance. The most classical one is to run a t-test. If you do run a t-test, look for p-values that are smaller than 0.01. If as a minimum, and if you can get a statistical significance below 0.001, then you are pretty confident that your algorithm is statistically significantly better than the state of the art. So aim for this, right? Aim for that statistical significance, but require to yourself at least getting this top one as a confidence that, okay, maybe I'm not much better than the state of the art or even better, but at least I'm not worse, right? Okay. All right, any questions about this? That's right, yes?
What exactly do you mean by statistical significance?
It means that if you run a test, like a t-test, a statistical analysis, right? There are many such tests. I'm not going to cover this. But if you run a statistical analysis, that means that when you change the training set and the validation set many, many, many times, supposedly millions of times, right? Your result is most likely to be better than the results of other algorithms most of the time, right? So one t-test that you can run, which is very simple, and you should always run, I mean, this is the obvious t-test that you should run, is that you can run your algorithm against random classification. And there are multiple ways to do that. You could have an algorithm that classifies objects randomly, or in regression gives random numbers, right, to your regressor. But you could also do that by scrambling the labels of your X, capital X, right? And the way you do that is you multiply the capital X, which is a matrix, right, or a tensor with the xi's and the yi's, such that the yi's get permuted, and there's such a thing called the permutation matrix, which is a diagonal matrix with all ones, where these rows have been interchanged, permuted, right? And now the yi's are misaligned with the xi's, right? So a table is labeled a car, and another table is labeled a chair, and another table is labeled a human, and another table is called a book, right? So now see how your algorithm performs on that task. And if doing many such permutations, right? So you have to do this many, 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 many times, at least hundreds, thousands, if you can thousands, and if you can tens or hundreds of thousands or millions, then you do it, right? And then you see how many times does this algorithm perform, or even better, how many times, what's the probability that this algorithm performs above a classification accuracy? Okay, and we'll talk about classification accuracy in a second. Say 50% classification accuracy or 60%. And maybe you come up that with this, any algorithm can perform above 60% accuracy 30% of the time, right? Now, if you run your algorithm on multiple subsets or data sets, right, for object recognition, is your algorithm going to outperform 60% classification accuracy more than 30% of the time? Because if it doesn't, then what's the point, any random classifier can do that, right? So at least you should be able to do that many, many more times than any random classification, right? And these are different ways of getting p-values, right? To get a p-value means the percentage or the proportion, rather, 0 to 1, right? Of how many times can I get this result by chance. So a p-value of 0.01 means that 10% of the time I'm getting my result that I have just by chance. 0.001 means that of every 100 times I run my experiment, 1 of these times I get that result just by chance because I was lucky. Right? If you had a p-value of 0.0001, it means that you have to run 1,000 such experiments to get that result by chance. Right? So the smaller the p-value means, the less likely it is that the result that you're seeing there is just that you were lucky. Right? Okay. All right, so this is all well said and done. There is one final data set that you hope, and you certainly should hope, that you have somehow access to, which is called the testing set. Okay? So let's see what that is. Because there is misconception about what the testing set really is. So remember that both the training and the validation set are visible to you. These are sets you have access to, and therefore you can play with it, and you can change your algorithm until it works on those data sets. Now, the testing set, let's call it T, is another labeled set. Let's call it now xi, yi, I from m plus 1 to, I don't know, capital T. This set is not visible to you, right? This is not visible to us. We never gain access to that data set, ever, right? And when I mean ever, I mean ever. Because even if you have access one time, right, to test, someone says, okay, finally, here's the test, test it now, then that's visible to you. That's no longer a testing set. That's a validation set. Okay? A testing set is a set you never have access to. And there are multiple ways that this can be done. This data set is usually, it's called sequestered somewhere by someone. And maybe it's in a server, and you can upload your algorithm into that server, and there is a routine that makes it run with that data. You never see the data because it's not your computer, right? And it keeps running there, and at the end of the day, it gives you some evaluation on that testing set. Great. Right? The other option is that the images or videos in computer vision are sent to you without the labels, and then you return the label, and then they tell you how well you do. That's not really testing, technically, because you see the images, right? So the labels are not visible to you, but you see the images. In that case, there's something that should be done that I don't know why it's almost never done, or probably never done, although we have done this, which is that you lie to people, right? You create placebos. This has been done for many, many decades in medicine, right? And what do they do in medicine? They have N patients, and half of these patients get the medicine, and the other half get a placebo, right? The sugar pill. And you don't know, you're lying to people because you don't know who gets a placebo, who doesn't. Neither does the doctor that gives you that medicine, right? They don't know if they're giving you a placebo or the actual medicine. They don't know when they collect the results. They don't know if you had the placebo or the medicine. It's only after the fact, when the data is compiled, that you know, right? So here's how you do this. Take the whole data, the testing data, right? If you're the person that has sequestered the data, you have the N samples, and for half of them, you evaluate them correctly, but half of them, you evaluate them randomly, right? Let's say that it's a two-class classification problem. Does this image contain a face, or does it not contain a face? And I keep giving you images, and you keep saying yes, no, yes, no, yes, no. In half of these cases, I actually use the YI to tell you whether your answer is correct or not. In the other half, I randomly say yes or no. Now, what is the best classification accuracy you can get in that case? Anyone? 75, right? 75, it's the best. So you know what the ceiling is, how well you can do on average, right? So you can still know how well you're doing. But on the other hand, you don't know for each image whether your response was correct or not, meaning you don't have the labels, right? You can never recover the labels, right? So there are mechanisms that can be put in place to make sure that you never recover the labels, right? The ideal one is you upload the algorithm in a server, it runs locally, you solve all the problems this way because you don't even see the images, right? Your algorithm does, but you don't. But in the worst case scenario, you can run experiments, placebo experiments like this, all right? Now, this is sequestered data, not visible to you. That is truly the testing data. It's also important that you only have access to this data set maybe once, maybe twice, maybe 3 times, but this is it. Because even if it's not visible to you, but you keep getting the results on this data set, even you don't see the data set, eventually you'll figure out a way to make it work, right? So the testing set can only be available to you in a very small, limited amount of times, right? Maybe it is, I don't know, once a month, right? Because if you have a project that has to be completed in 2 years, even if you have access to it once a month, maybe it's okay. At the end of the day, you are going to use it at tops 24 times, right? But if you have access to it every week, then all bets are off. Because then you're going to overfit anyways. That's what I called overfitting to the testing data. And then it doesn't matter. We saw this in the early 2000s. I was very much involved in face recognition of identity. And we saw this because we kept collecting data sets for face recognition. And people would apply the algorithms that they had already developed over the years to the latest data set, right? And the results were like 30% accuracy. And then after 6 months, people were at 50%. After a year, they were at 80%. After 2 years, they were at almost 100%, right? And by that time, someone had collected a new data set. And then people would take these algorithms like, oh, these algorithms already work. And they apply to the next data set 30%. And then after 6 months, 50, after a year, 80, after 2 years, 90, 95, another data set would come up, 30%. And you kept seeing this sinusoidal. And I was like, at which point are we going to realize that we're not making progress, right? At some point, you have to stop and say, wait a minute, this is not working. And that's a problem, right? That you have to never have access to the testing set because otherwise all bets are off. Okay, any questions thus far? So let's move on to then evaluation. How are we going to use all these to evaluate our system? So call it benchmarks. Ways to evaluate the system. All right, again, this would have to be a 10-lecture course, right, rather than a few minutes. Yes?
If you rarely ever test with your testing set, but say your algorithm starts doing very well with your training set and your validation set, but then performs poorly on your testing set. How do you know how to really change your algorithm then? Because as you keep testing it and changing it.
Very good question, right? If that happens, let's say that you get a 99% accuracy in your validation set, even with k-fold cross-validation, and then you test it on your testing set, well, on someone's testing set that has been sequestered, and you perform at 10%, then what you'd suggest is scratch that algorithm, right? You're doing something fundamentally wrong. You design an algorithm that is specifically tailored for your validation set. Reconsider what you were doing. You're doing something that is fundamentally incorrect because it's just not working, right? I mean, you have to be extremely careful with these things. I mean, just to give you another anecdote, right? There was, and we'll talk about this, years ago, a competition for object recognition called ImageNet, right? Pascal VOC, ImageNet, we'll talk about all these things. And Google, research at Google, one year they won with a deep neural networks called GoogleNet. And they were convinced that they had solved the object recognition problem. And I kept saying that that's absurd. How can you claim that you have solved the object recognition problem? The object recognition problem has not been solved to this day, let alone back then. What you have solved is partially, at least, the ImageNet problem, which is not the object recognition problem, right? But they were convinced, they were adamant that their system worked really well. So they convinced someone, I don't know how they managed to do that, to put that system online on the Google website. Within minutes or hours, just a few hours of that system being online, a reporter from, I think, the Washington Post, maybe some other newspaper, I forget, but I think it's the Washington Post, went online, uploaded a picture of an African American, and the system returned the object that it had recognized, gorilla. Wrote an article about this, posted it online. That system has never been online ever again. That system went down within the minute from that article appearing in the Washington Post, right? Like, yeah, are we surprised? I wasn't surprised. What surprised me was that other people were surprised that this would happen. Yeah. We have to know what is the problem that we are addressing, right? Remember what I said, point one, define the problem. If your problem is to solve the ImageNet classification problem, then that's fine. But then be realistic. That's what you have solved. You have not solved the object recognition problem. That's a very generic problem. That's a very complicated problem. That's what I mean by all this. So, does this mean that that system is useless? No, I mean, Google uses this system all the time, right? If you have, for example, Google Photos, they use it to this day. You know, you can Google Photos, you can go there and search for, I don't know, people running or mountains or what have you, right? Houses. And it'll give you images and, you know, it's not great, but it works okay. But to this day, there is one keyword that the system doesn't accept. Gorilla. Not even Google, with all its resources, can solve that problem, right? That's how hard it is. So, but at that point, I think that they made the right decision, say, okay, that keyword is out. We can solve it. Well, then we can solve it, but be realistic. So first, be very careful with these steps. But then if you do something and you crash, like this bad, then reconsider everything that you have said or done, right? Yeah, makes sense? All right. Where was I? Oh, benchmarks. So evaluating computer vision systems is hard, let's face it. As I said, I covered this in machine learning in more detail, but let's see a few obvious systems or metrics that we can use, okay? Now, the most classical way to evaluate the system is to use the so-called square loss or square function, which you also know it by another name, anyone? least squares, right? So the least squares loss, obviously, it's the most classical way. So you're going to compute the error function, right, of your algorithm by 1 over what was it? N, right? The sum over all I 1 through n. Actually, we had m plus 1. Let me do that. And we had from m plus 1 to capital T, right, for the testing, right? We had this. So this is going to be divided by T minus m plus 1, right? Yeah? Okay. Let me do it a little clearer. M T plus 1. Whoops. Oh, my gosh. Oh, sorry. 1 over m minus T minus 1. Okay, I'll do that. From m plus 1 to t of f of xi, right? Where f here is your algorithm. So f is the output of your algorithm. Remember, my algorithm is a functional mapping f of f that for each f of xi gives me an estimate, let's say, y hat, right, of the output. And I'm going to subtract this guess, right, that I make from the actual ground truth, so-called ground truth, or the true label, right, of my data set, and then square that, right? And this is the either the square loss or the least squares loss or function or error function, right? And generally, we're going to call this the the testing error. Now, the testing error will be given by this equation. Of course, I can change this equation to compute the training error and the validation error, right? So for example, the training error, let me call it, I don't know, ETR, right? It's going to be 1 over n, the sum from 1 through n of fxi minus yi square, right? And this 2 means the 2 norm, right? Right? And the validation error would be the same one, but then here be the number of validation samples, right? Yes? Okay. So this is the training error, and correspondingly the validation error. Now, of course, no one forces you to use the 2 norm, right? What are we going to use the 2 norm? Right? I mean, is the 2 norm better than the 1 norm? Is the 1 norm better than the 10 norm? Or why not use a quasi-norm, right? So in general, you could use any norm. So you could define 1 over n for the general case, f xi minus yi of p square, where p specifies the p norm, right? It could also be a quasi-norm, right? I remember that quasi-norm is when p is larger than 0 but smaller than 1, right? So remember, the 2 norm is the circle in your space, right? If we have r dimensions in our space, right? If our space is of r dimensions, meaning these vectors are of r dimensions, right? Then the 2 norm is the circle. The 4th norm, for example, it's closer to this, right? To a ball that is being inflated, right? The infinite norm would be the absolute square, right? The 1 norm is the rhomboid here, right? The rotated square. And the quasi-norm will look something like this, right? Yep. Remember all this from 5460? Okay. If you don't remember that, look at the video lectures of 5460 when we talk about norms, okay? Because that's very important to understand how you are evaluating things. Because people many times say, well, you know, I'm just going to use the true norm, and my algorithm works better. Like, yeah, on the true norm, but is the true norm what really evaluates your algorithm the best? I don't know. Maybe it is. But you know that first step that I said, define the problem? That's what you have to go back to determine how to evaluate the system, right? All right. So these things and variations of that, you know, you could use a nuclear norm that we've talked about, the so-called zero norm, which is not a norm, and so on. All these things, you could use them to evaluate a system, and they are especially good when your yi's are in the real domain. Okay? Meaning regression. Now, if your yi's are natural numbers or integers, then in that case, most typically, you want to use the 0-1 norm. Okay? I'm sorry, the 0-1 loss. Okay, and the 0-1 loss, it's given by 1 over n, the sum of all my samples from 1 to n of, I'm going to use this big 1. This is a 1 with some special font. Fxi, comma, yi. So this is a function, right? A function that has two inputs, f of xi, the output of my algorithm, and the true label, the ground truth, right? Where now this function, what this function returns, excuse me. What this function returns for AB is it returns 1 if A is equal to B and 0 otherwise. Now, you can see why this is useful for classification problems, right? So I'm going to use that especially in classification. Because in classification, I'm not interested to know what's the distance between the expected number and my estimate, right? So if tables are number 1 and chairs are number 3, and I guess table, but it really is a chair, why is that difference 2? But if I guess a book, which is number 10, that difference is 9. It just makes no sense, right? What you want in classification is, did I get the actual label correctly? If I did, I add 1. If I didn't, I add 0, right? Actually, that should be the opposite, right? I've just realized. I'm sorry. It should be, if we're computing the error, this would be for accuracy. What I wrote here is for accuracy, right? But for the error, it should be the other way around, right? If I do correctly, no error. If I do it incorrectly, I add 1 for error, right? And I get the proportion of my errors. You see that? Okay. All right. For binary classifiers, and we're going to be you're going to be using this a lot, because many things many algorithms in computer vision are designed for binary classifiers. Binary classifier is an algorithm that decides whether an image or video sequence has that class or that category or it does not, period, right? So for example, as I said earlier, an algorithm that determines whether an image contains a face or it does not contain a face. That's it, right? That's a binary classifier. Now for binary classifiers, you want to use something else. You don't want to use either of this that we have derived here thus far. You want to use another set of metrics. What we're interested in binary classifiers typically is we want to know the number of what's called true positives, true negative, the true positive and true negative, as well as the number of false positive and false negatives. Okay? Let's see what these are. To see that, let's draw a table with 2 rows and 2 columns. Okay? And here I'm going to have, say, the target class, right? Or the positive class, like a face, that's a face. And here's the not the target class, right? So not a face. And here's also the target class. And here's not the target class. Okay? Now let's say that these 2 rows specify the output of my algorithm, right? The output of my computer vision algorithm. Okay? That's the output of my f function, right? And over here, I have the ground truth, right? Okay? The actual true label. Okay? All right. So now let's see how this works. Now, if the true label is the target class, right? Say a face, and my algorithm says that there is a face, that's a true positive. That means that my algorithm correctly predicted the true class. Okay? Now, if that image or video does not have that class, that's a true label, it doesn't have, say, a face, and my algorithm says that there is no such class or target in that image, that's a true negative. So far, so good? All right. This makes sense. Now, if my algorithm, however, says that there is a face, that there is a target class, but the image does not have it, that is a false positive, right? Because I say that there is such a class, I say it is a positive, but it is not. You will see also in the statistics this many times is called a type 1 error. And if my algorithm says, no, there is no such a thing as a face or as that target class, but there is, then this is a false negative. Okay? And in the statistics, this is sometimes called a type 2 error. Okay? All right, perfect. Now, if you're working with binary classifiers, you should plot this table if you can, right? Now, this table is very informative because it tells you when the algorithm works and when it doesn't work, why it doesn't work, right? Now, the most classical way to summarize this table is by giving 2 measures of an algorithm. One is called precision, and the other one is called recall. Okay, so precision and recall. Let's define these 2. So, and recall. Now, precision, sometimes it's called positive predictive value as well. Precision is the number of true positives divided by the number of true positive plus false positives. Okay? So precision is true positives divided by true positives plus false positives. Okay, why do I do that? Because, look at this. I'm interested how many true positives I have, right? But there is a really good way to get 100% of the true positives. This is an algorithm that always says there is such a target in every single image. If I always say there is a face, then I'm going to get all the true positives. That's going to be perfect. But I'm going to have a lot of false positives too. That's why I divide by the total number of true positives and false positives, right? That's how precise I am. What I want is to have only true positive, all the true positive, and 0 true negatives, right? And in that case, false positives. And that is the case when I get a perfect score of 1 in precision, right? Okay. All right, recall, on the other hand, computes the number of true positives divided by the true positives plus the false negatives. And now in that case, we're looking at this column, right? All right, how many true positives do I have versus how many did I miss, right? Because the opposite could be true, right? I always say, well, there's never a face, right? Now, a face may be something really absurd to talk about, but let's say that I have a camera looking at the highway, like 315 right here, right? And it's just looking at that highway. And in the middle of the night, when there are almost never cars on the road, right? My algorithm always says there are no cars. Well, most of the time, my algorithm is going to be correct, right? But that's what I'm interested in knowing. Not the true positives, but the true positive divided by the true positive and the false positives, right? And then the more false positive I keep adding, the more recall I'm going to get, right? Okay. This is still 2 numbers, though. A way to combine these 2 numbers into a single one is to use the F beta score. And this is just a very convenient way because instead of having to report 2 numbers, you just report 1. So it's called F beta score. And F beta is defined as 1 plus beta square times precision times recall divided by beta squared times precision plus recall. Most people use a beta of 1, which leads to the F1 scores. Okay. F1 will be 0 if your algorithm only has false positive and false negatives, and it doesn't have any true positive or any true negative, right? And it will be 1 if it gets all the true positive and all the true negatives correctly, and has no false positive and no false negatives. Okay, one final one, very important. A final measure to use in binary classifiers is to provide a plot of the true positives, or the positive rate, rather, over the true positives. And this is called the receiver operator or operating characteristic function or curve, or most commonly called the ROC curve. Okay. And what we're going to compute is here on the x-axis, the the false positive rate, which is given by the true negatives divided by the true negatives plus the false positives. And on the y-axis, I have the true positive rate, which is given by the true positives divided by the true positive plus the false negatives. Okay? All right, let's think about this for a second, because it's important to understand how this works. Now, if I only have all the true positive and I don't have any false negatives, right, this is going to be 1, right? Correct? So that means at 1, it means I get all the correct true positive and I don't get any of the false negatives. Here, if I'm at 1, that means I get only true negatives, right? And I don't get any false positives. You see that? Right? So what that means is that if I create a square here, that means that this diagonal line, anything that's below that diagonal line, is impossible to occur in any classifier, right? Because that is for binary classification, and that would mean that if I'm down here, the classifier performs less than 50% accurate, right? I'm maybe at 49, 47, 40, 30, 20%. But in a binary classifier, that's impossible. Why? Because if I just design an algorithm that says the opposite of what my algorithm says, I'm all of a sudden up here, right? So if I'm 30%, by just saying not what my algorithm says, I'm going to be at 70%. It's absurd. It can never happen, right? So this area is never possible. So in an ROC curve, you always have to have something above that diagonal, okay? And then what you're going to have a curve. This is why it's called an ROC curve that looks, actually let me use this other color, that looks something like this. And what does this mean? That means that the true positive rate is going to increase with the true negative rate. And that makes sense, right? The more errors that I'm allowing to make, the more positive, the more correct classifications I'm also going to get, right? So if my goal is to detect faces or cars in a highway, right? Cars in a highway, the more that I allow to make mistakes, the more likely I'm going to be right, because I say that there is a car more often, right? In the last case, right, when I allow to have all the false positives, then by definition, I also get all the true positives, right? By definition, because I always say there is a car. And in that case, I have 1 on both, right? So this curve always looks like this. What you want is a curve that is as high as possible, right? And ideally, the ideal curve will look like this, right here, and then like this, right? That's the ideal curve, which is theoretically perfect, practically generally impossible. Now, a final measure that I just want to comment that you can use then to measure how good your binary classifier is on an ROC curve. Obviously, you can plot the curve and visually look at this, but there's something you can do. You can compute the area under that curve, right? And the area under that curve, it's the, if I integrate this curve, right, here, this A It's the integral, right, over this dx and dy of my function, right, of my ROC, right, of my ROC curve. And if I integrate, I get this area, and the bigger the area, the better, right? You see that? All right. So this is it for designing systems and evaluation, and we'll start talking about the specific types of object recognition starting next week. Okay? See you then.